In the 1980s, driving from Paris to Spain meant hitting a massive geographical dead end in southern France. Holiday traffic was forced off the highway and down into the Tarn River Valley, a jagged 1,500-foot deep gorge. This topographical map shows exactly why the valley was a nightmare. Vehicles navigated a steep zigzag descent to reach Millau at the bottom, only to crawl back up the other side. This trapped drivers in gridlock for 6 hours. To relieve the pressure, the French government proposed a radical fix: bypass the town entirely by building a highway straight across the void, from one mountain peak to the other. Bridging this gap meant suspending a heavy roadway nearly 900 feet in the air. For scale, the road deck of the Golden Gate Bridge sits 250 feet above the water, 6 times lower than required here. Suspending a 4-lane highway at that altitude exposed the structure to devastating crosswinds whipping through the gorge at 130 kilometers per hour. Many engineering experts reviewed the sheer height and extreme weather and concluded the bridge was physically impossible to build, warning that attempting it would invite a catastrophic collapse. The task of designing a structure that could survive these immense forces went to British architect Lord Norman Foster. He drafted a cable-stayed bridge with a remarkably slender profile, intending it to slice through the harsh mountain winds with the delicacy of a butterfly. But Foster's reputation was already hanging by a thread. Just a few years earlier, his highly publicized Millennium Footbridge in London had to be closed shortly after opening because pedestrian foot traffic caused the entire structure to sway violently. Despite the heavy skepticism, in October 2001, a French construction firm agreed to execute his design. They signed a contract with a brutal ultimatum. They had exactly 4 years to build the tallest bridge on Earth. Missing that deadline meant a firm would be hit with a punishing fine of $30,000 for every single day the project ran late. The team was now racing against the clock. They had to invent completely new construction methods to conquer the valley, knowing that the slightest delay would drag them into total financial ruin and professional disgrace. The problem started the moment they broke ground. Geologists analyzing the soil discovered that the foundations were sitting on top of fractured limestone, an area heavily riddled with deep, hollow caves. Before they could even address the unstable ground, the earth gave way. A massive landslide tore down the slope and completely buried the excavation site for the very first pillar. Scrambling to save the timeline, the crew performed an emergency intervention. They pumped huge volumes of cement directly into the fractured slope to artificially stabilize the mountainside so digging could resume. Once the bedrock was secure, they began casting the bridge's 7 massive columns. This required pouring 200,000 tons of steel-reinforced concrete into uniquely tapered molds that had to be constantly resized as the pillars climbed higher. This structural diagram illustrates the terrifying geometric trap they faced. Because the tallest pillar would reach 245 meters, even a tiny 10-centimeter misalignment down at the base would magnify into a massive 6-meter gap by the time it reached the top. To prevent this, the engineers discarded standard surveying tools entirely. Instead, they relied on multi-satellite GPS targeting to perfectly align the 15,000-ton steel casting molds for every single concrete pour. They achieved perfect vertical alignment, but fighting the shifting earth and the constantly changing concrete molds burned critical time. By the time the massive towers were finished, the team was 6 full months behind schedule, pushing them dangerously close to the penalty phase. By November 2003, the concrete pillars were standing at their final heights. Now the crew had to figure out how to put a 36,000-ton, 2.5-kilometer-long steel highway on top of them. However, traditional bridge building techniques were completely useless here. There was no crane on the planet capable of hoisting 5,000-ton sections of solid steel 800 feet straight up into the air. The standard alternative is pushing the deck horizontally out from the mountainside. But as this animation shows, forcing that much weight horizontally drags against the tops of the pillars. The extreme friction acts like a lever, bending the slender concrete columns inward until they shatter. To bypass the friction problem, the engineers brought in Eiffel Steelworks. They engineered a completely novel machine, a specialized hydraulic lifting system mounted directly on top of the concrete columns. This shows exactly how the wedges worked. Instead of dragging the steel, the hydraulic rams physically lifted the massive deck off the pillar, pushed it forward in midair, and then carefully set it back down. But this lift and push sequence had to be executed simultaneously across all 7 pillars. If one hydraulic ram fired even a fraction of a second too late, the uneven distribution of weight would crush a single pillar and bring the entire bridge down. The future of a billion-dollar megastructure now relied entirely on an untested, custom-built system, blindly walking the equivalent weight of 90 commercial airliners over an 800-foot drop. Pushing the deck forward was an agonizingly slow process. The operation was strictly limited to days with absolutely pristine weather, as a sudden gust of wind catching the unsupported overhang could easily twist the steel and rip the bridge apart. Inch by inch, the massive steel sections crept out from opposite sides of the valley. Finally, in May 2004, the heavy north and south stretches of the highway met midair directly over the Tarn River. The opposing sections slotted together with a 99.9% rate of accuracy, a flawless connection observed on live television by the French Prime Minister. With the deck safely locked in, the crew raised 7 700-ton steel pylons to anchor the upper suspension cables and laid down thousands of tons of heavy asphalt. When finished, the total suspended weight of the roadway hit a staggering 50,000 tons. To prove the design was safe, the engineers parked a tightly packed convoy of 28 heavy industrial trucks directly over a single span. The massive load caused the deck to deflect downward by only 25 centimeters, exactly half of what the bridge was engineered to withstand. Opening to the public weeks ahead of schedule and entirely dodging the financial penalties, the Millau Viaduct team solved a notorious traffic nightmare. They shattered the known limits of structural engineering to build a permanent 120-year monument that quite literally floats above the clouds.